how it is in reality. This is now really with a full wave packet. And you see essentially we don't come further but one full reflection. Then it just, yeah, disintegrates if you wish. Okay, but that's work in progress. Now I want to switch gears a little bit. I don't know, be faster to let you off the hook. And come now from single atoms to atom clouds. So far we had really single atoms. And I will use the interaction blockade and check out if one can use the interaction blockade to actually do not have to prepare single atoms for this kind of excitonic transport, but maybe could use one cloud, the next cloud, instead of individual atoms, yeah, which is maybe much easier. And we will also see what Rydberg dressing does. Okay, interaction blockade you know by now. Of course, it's that you lose the resonance if you try to excite another Rydberg atom due to their strong interaction, and therefore you can only excite one. That's kind of the range of the whole thing. And now let's apply that. So we do now a single excitation in ground state ensembles. So we have two van der Waals blockaded ensembles with a single Rydberg excitation. Remember, single Rydberg excitation for me always implies a single P excitation. And of course we have in the other cloud a single S excitation, but then I call it ground state. But this gets a bit confusing because now we are really interested in the ground states. Yeah, the ground states are kind of the open circles, and we have now one S Rydberg excitation, one cloud, and one P in the other one. And it's done like that, that you have basically a situation that the blockade radius is larger than the extension sigma of each of these clouds, but of course the separation of the two clouds is much larger than the blockade radius and the extension of the clouds. Alright, now question to you. You know that this is basically kind of a almost collective state. It's distributed over all the cloud, superatom, yeah, blockaded atom. And we know we have an excitonic-like excitation, so we can prepare a repulsive state, linear combination of S and P. So they two, if they would be individual Rydberg atoms, they would repel each other, right? That we saw before. Now do all the two clouds repel each other completely or not? What do you think?
Actually, we don't know which atom is really excited.
Right.
So it's a superposition of
Right.
all the cloud. So
Right.
I think that probably the cloud will.
The cloud. That's also what we thought, but it's not true. Or we thought exactly the same thing.
So,
I mean, it's only, after all, it's only single excitation. Maybe we can rationalize it in this way, yeah? And so, actually the single excitation gets kind of localized and decides to expel two atoms. And at that point, you can identify them, and it's kind of, yeah, the superatom breaks at this point. But, yeah, it's not so trivial. So you see that here now already with 3 atoms, and that demonstrates to you that this cradle now works really with like ensembles. Yeah? So each of these peaks now is basically one little ensemble of atoms with one Rydberg atom in each one. And we again create an exciton here, closer by. So red indicates that we have P combination here, and we let this run. And you see what happens, hopefully. Aha. Now you see, right? There's something sticking behind, and that's all the ground state atoms. And all the ground state atoms is only one, because our great ensemble consists only of 2 atoms. Therefore, it's the same height here, yeah? So the excited one gets repelled, and the ground state atom stays behind. This you see also here in the traces. But the nice thing is, you can continue with the motion, and indeed it behaves as you hope. This one kicks the next one, and the excited one gets kicked out, and the ground state one stays behind. Yeah? So it's really only the excited one which is affected and gets moved. But in the same way, coherently in blah blah blah, There might be losses because there are the ground state atoms around now. Of course, you have collisions and so on, but this was very small, so there is no problem. All right. So this seems to work. So that means we can make this excitonic transport by using the blockade effect with ensembles of atoms. We don't have to prepare individual Rydberg atoms. But now, and I think this is the last thing already, more or less. Yeah, this is just where you see once you get the matrix here, the interaction matrix, dipole matrix, that really it's only a single pair, right? Because the interaction matrix is block diagonal. This is shown here for the enormous number again of 2 atoms per cloud. And in cloud A is atom 1 and 2, in cloud B atoms 3 and 4. And if you then, so you have one ground state atom here, one excited one, same thing here. And if you calculate the interaction matrix, you see it's nicely block diagonal, so you have all 2 by 2 copies. It's just individual excited atoms. V naught is the strength, it's just mu squared dipole strength. So, and this is something I think Charles asked me or wanted to know. I don't know if he's here, no, maybe not. What is the dephasing? The electronic dephasing, and the electronic dephasing is now basically can be calculated as a sum over static pairs of virtual atoms with slightly different distances. So what should happen, of course, that you have now Rabi oscillations because the excitation, yeah, the P migrates from, where's the P? The P is here, I think. Migrates from here to here and back and forward. Yeah, that's a normal thing. And you have basically a loss of this nice Rabi oscillations because the distances between all these pairs in the linear combination, these virtually excited pairs, they are not equal. They are only equal within this Gaussian width, but they're not truly equal. And therefore you have dephasing. And this can be calculated very easily. So of course it goes fast. You can fix the atoms. And then you simply have your electronic wave function as a diabatic representation here, sitting on the atoms with this differential equation. And this gives you immediately then the probability to find atom 1 in an S and let's say atom 2 in a P state, like this. This is our Rabi oscillation. And the only thing is now what we have to do. We have to basically integrate over all different separations of these 2 excited atoms, which are slightly different from L. Yeah? And this is done here, and if you do that and make the right approximation, and that is Taylor expand here, this L cubed to first order, then you get analytically this expression, which tells you how fast basically your Rabi oscillation decays. And it decays basically with an exponent which is proportional to the width. This is to be expected. If there's a larger width, then you have more variation in the distances of your interactions. And of course, what helps you if they are more distant, the 2 clouds. So therefore this is in the denominator here. And then you see here, so this is the result. It decays relatively fast. Below 1 microsecond, you just see 1 or 2 oscillations. And I think this was for this kind of parameters. For, yeah, if you want to translate it into something halfway real, this is lithium atoms. We always love lithium atoms because they are light and they are propagating fast, yeah, I mean on the computer. And so interaction strength is like this, and the distance was 6 micrometers, width like below 1 micrometer. And here 1 is the quantum solution just for a pair, and I think the dashed one and the crosses, that's the same. This is this static average over all the different distances in the cloud. So that really agrees quite well. Okay, now the question is, and we just learned that essentially if we have 2 clouds, then the superatom breaks the blockade atom, and really only the 2 individual, or not the 2, because we don't know which ones, but 2 individual works of atoms get expelled, get kicked out. Now, how can we restore basically this collective motion? So, can we actually redistribute kind of this excitation to all the atoms, also all the ground state atoms in the cloud, so that eventually, really, the two clouds completely move apart or together. How would we do that? This we can do by dressing, right? So this is now the last thing I want to tell you. And you learned already about dressing yesterday from Matthias, I think. So the idea of dressing is simply that you do not couple resonantly now with the laser two levels, but you go off resonance, and that results basically into a mixture of your excited state to your ground state, or from where you start. And the strength of this mixture is just given, or can be tuned, essentially here by your laser parameters, by how far away you go with your excitation from the resonance and how strong you drive the transition. And of course it depends on the dipole moment as well. But essentially you can kind of tune the size or the extent of your admixture. And this has nice effects. It increases normally the lifetime of the Rydberg state, yeah? Because it quenches the interaction. If this amplitude is much smaller and two Rydberg states interact with each other and decay or so on, then of course it's smaller by alpha to the fourth. And this is used in most applications, at least in the ones we do, to make these Rydberg things possible. But here, now we actually use it for a different purpose. We want to bring the ground state atoms into play, yeah? Because we want really to address the entire, or all the atoms in the clouds for our dynamics. So how do we do that? We need actually double dressing, because we want to image kind of our SP, Rydberg situation into a ground state situation, and that's now two hyperfine splitted states of the atom, and both of them get dressed. So the true ground state, let's say to the S state with a certain offset, and the hyperfine splitted, little bit excited state to the P Rydberg state. And once we do that, we get basically this kind of coupling term, and indirectly what happens is really that the dressed ground states GH, the pair, inherits now the Rydberg SP repulsion or attraction. Yeah? In the Rydberg pair, everything is as we used to. So we get repulsive and attractive surface. But this is now through dressing inherited by our ground state atoms, so they also experience now a force. And that's what we wanted. Now, all of a sudden, all the ground state atoms also participate in this dipole-dipole interaction induced force. And what I show you now is an example, I think, for rubidium 87, superfine states, a dressing which leads to basically coupling, mixture of alpha 0.15. This is the dipole moment, and there was n equals 80. And now also you see, for illustration, the dipole-dipole coupling matrix looks really very different now. Yeah? Before we had block diagonal 2 by 2 here, and now we have a totally different structure which tells you everything gets really involved and coupled. And the nice last application I want to do, just for the fun of it, is of course, we know that essentially we can now spatially move atoms and keeping their coherence, their individual coherence. So something which of course comes to mind immediately is to create a cat state, a Schrödinger cat state, which is like spatially separated. Yeah? Of course, normally a cat state dies immediately, decoheres and so on if you do anything to it, try to measure it, observe it, or manipulate it. But, and this again, and that's my final verdict, through letting these natural forces act on the atoms induced by the electronic excitation, you don't do anything from the outside, and that preserves coherence, and therefore you also can create a kind of microscopic, or at least mesoscopic cat state where the two components really move spatially apart from each other. So what we do is we basically construct a cat state between the attractive surface and the repulsive surface, and I should show that here to you, maybe if you're not familiar with cat states. So a typical cat state is such a linear combination, and of course it's more and more cat-like if there's many more atoms or states or systems in the same state in linear combined with the other one here. But of course, this is very, very susceptible to any kind of decoherence in destruction. And most of these cat states are therefore realized in superconducting circuits as spin states. So really, these basically quantum numbers are then just spin states. They are not spatial, because spatial is very difficult. And we now try to basically realize that in a spatial domain, and I don't want to tell you that how this goes. Technically, it's a little bit involved, but the first step is you create a fully coherent repulsive spin state from your ground state here through a microwave field. And then our friends from quantum information have thought about many, many ways how to convert basically these kind of entangled states. And there's one way where you can convert this repulsive state into an attractive one. And then we have basically both the attractive and the repulsive one. And this then creates here our cat state, the superposition. And now we know what happens. The repulsive one, the atoms move apart. The attractive one, the atoms move together. And this is exactly what happens, yeah? So we have our two clouds. And now basically one part of our cat state moves together and the other one moves apart to the outside. And really you get a separation here. And this separation is periodic because it's still, it's still in a trap. I mean, each of the cloud is of course sitting here in a trap. And therefore it should oscillate. And that's kind of the last transparency. So after half the trap time, they are maximally apart, these two components. No, sorry, after a quarter, of course. I mean, a quarter go out, and after half, they come together again. This is shown here. And then these two components really should show interference if it's completely coherent. And this is all the atoms really should move there through the trap. So that's the proposal. And this is how much you lose through preparing the whole thing through the initial acceleration here when they start to move. And this should be relatively small. The referee requested that, so we calculated that. Okay, so we have turned this little cat into pussycat into a real impressive, hopefully, tiger. And with that, I would like to close and thank you for your attention.